So this is basically the third lecture of this potential flow. We have two lectures and we have seen certain basic idea about what are complex potential functions. Okay, how different flows can be visualized using any simple complex potential function. We have talked about all these things. Okay, then we will now move on to some other things like the vortex flows and all. So let us see. We will discuss the case of vortex flow and circulation in this lecture, and also we will see the superposition of flows. Okay, so we have seen one superposition already. If you superpose a source and a sink, that gives a doublet. We have seen that. Now we'll also see the case of a Rankine half body. Okay, so if you quickly revise, we have seen in the last lecture we have seen the complex potential functions for case of for n equal to 2, n equal to 3, n equal to -1, n equal to -1/2. We have seen the flow in a sector, and after that we have talked about the complex potential functions of source and sink, and we have defined what is tenth of a source and of course tenth of a sink also, and we derived the complex potential functions. Okay, and then we have seen the superposition case of both of them, and we have seen the case of a doublet. Okay, so let us write the complex potential functions once. So for uniform flow, inclined at an angle alpha to x-axis is given by f of z. F of z is equal to half f of z is equal to u times e power minus I alpha times of z, correct? So let us suppose if the flow is moving with some velocity u and if it is inclined at some angle alpha, then we have seen for flow in a sector, this f of z is given by this function. F of z is given by u times of z power n. Okay, so then we have seen some cases that whenever n equal to minus half, this is flow past a sharp edge. So flow past a sharp edge. Okay, and when n equal to -1, now you have understood this gives the case of a doublet. What is doublet? Source and sink of equal strength placed very close to each other. Okay, now we have seen other cases also when n equal to -1, n equal to -half, then n equal to 2, n equal to 3. We have seen such cases. Then we also talked about for source of strength m, at z is equal to z0. At z is equal to z0, we have f of z is equal to m by 2 pi log z minus z0 to the base e, correct? This is what we have. And of course for sink of strength m, again for sink of strength m at z is equal to z0, you have your complex potential function to be f of z is equal to minus m by 2 pi log z minus z0 to the base e, correct? So these are the complex potential functions in case of source, sink, and this flow past a sharp edge and a doublet. Okay, now we have seen the superposition of these two, so we have seen the case of a doublet, correct? So let us see. Let us continue the discussion from doublet. We have seen, so doublet is basically combination of source and sink, source and sink placed of equal strengths that are placed close to each other, correct? We have seen that. So now if you see, so in last session I have given you some mathematical understanding of the complex potential function. So if you see carefully here, let us suppose if this is a source and a sink, for example. Okay, so this is origin, for example, in the system. Then here we have a sink actually, and here we have a source, for example, and this length we have taken as epsilon. Okay, so this length we have taken as some small epsilon, some small length epsilon. Similarly, this is also some epsilon, small lengths. Okay, and the strengths are equal of both, say, source and sink. This is also plus m and this is minus m, for example. Okay, so because minus is because of it can actually take the fluid. Okay, so here we have seen one thing, f of z, the complex potential function, the complex potential function f of z is given by c by z. Correct. So this is the complex potential function. So these are the points that we discussed in the previous session. Correct. Okay, now let us try to see what are the velocities, how to draw the streamlines and all in this case. Okay, so let us see here. This implies f dash of z is equal to minus c by z square. Correct. So this is minus c by z square. So minus c by z square, if you write, this can be written as minus c by r square into e power minus I times of 2 theta. Correct. This is what you can write actually. So this can be written as minus c by r square times of cos 2 theta minus I sin 2 theta. So if you simplify this, we get minus c by r square cos 2 theta minus of minus plus I into c by r square sin 2 theta actually here. Okay, so this is sin 2 theta. Now try to see, obviously you know this is the potential function phi of r comma theta, and this here is stream function of r comma theta. Okay, so stream function of r comma theta. So that's how we have the case f dash of z. If you, sorry, I'm extremely sorry, this is ur, because this is the differentiation, right? So let us keep the minus sign as it is. So if you keep the minus sign, you are okay, fine. So let us keep it like this, for example. If you keep it like this, let us try to write this in one standard form. So let us see here, because this is f dash of z, okay, derivative. Okay, so whenever this is the derivative, minus c by r square into this e power minus I 2 theta, let us write this as e power minus I theta multiplied with e power minus I theta. Okay, so now if you expand this e power minus I theta, we have c by r square times of cos theta minus I sin theta into e power minus I theta is what you have here. Correct. So that's what you have. Basically this minus 2 times of I theta, we have written as one I theta and another I theta. Now if you slightly expand this term, we get, okay, I think we need some slides, just a minute. Fine. So see here, therefore f dash of z is equal to, f dash of z is equal to, from this, minus c by r square cos theta minus c by r square cos theta minus c by r square sin theta minus I times of minus c by r square sin theta into e power minus I theta, because we need this e power minus I theta combination to write the velocities. Okay, so from this you know that this component which is here is radial velocity, and this component which is here is azimuthal velocity u theta, and therefore ur is equal to minus c by r square cos theta, and this minus u theta is equal to again minus c by r square sin theta. Correct. So this is what we have. So these are the velocity components at any given location, means at any given point. These are the expressions for the radial and azimuthal velocities. Okay, and also you have this quantity f of z. We have f of z is equal to c by z. Correct. So this can be written as c by r into e power minus I theta. Correct, because z can be written r into e power I theta. So r I am keeping it in the denominator, e power I theta I am shifting it numerator with a minus sign. So if you simplify this, c by r times cos theta plus I times of minus sin theta. So if you expand this, we get f of z is equal to c by smaller cos theta plus I times of minus c by smaller sin theta. Correct? So this is what you have. Now try to understand this. This part which is here, the real part is the velocity potential function, and the imaginary part which is here is the stream function in this case. Okay, so psi of r comma theta. Now if you try to plot streamlines, look what you will get. Along a streamline, psi is equal to constant. Correct? So along a streamline, psi is equal to constant. So this implies minus c by r times sin theta is equal to some constant c1. Okay, now if you multiply this minus sign here and if you divide this with c, then also it's a constant. Yes or no? Means basically if you divide both sides with minus c, this minus c gets eliminated and c1 by minus c is again some constant. So let us write this as sin theta by r is equal to some constant c2, for example. Now what does this equation represent actually? Any idea? What does this equation represent? R is sin theta by r is equal to c2. Any idea what does this equation actually represents? Look, this actually represents a circle. Okay, why? I'll show you. Sin theta by r is equal to constant. So let us write that c2, if we shift here, some constant c dash, for example, is equal to r. Okay, so this is what you have. Okay, for example, if you shift this r here and c2 here, this 1 by c2 is some constant, some arbitrary constant. So that c2 we are writing as c dash, for example. Now what we'll do, we'll multiply one r on both sides. Okay, so you multiply one small r on both sides. Okay, so this gives you r square minus c dash times r sin theta is equal to 0. Okay, so this equation, if you simplify, r square is x square plus y square is the modulus minus c dash times of r sin theta is y actually. Okay, so this is y is equal to 0. So this equation can be written as x minus c dash by 2 whole square. Okay, so this equation can be written as x square plus y minus c dash by 2 whole square is equal to c dash by 2 whole square. Yes or no? Correct? Normally you can write this in terms of a circle equation, because this y square minus c dash y, you can write it into, if you try to write this in some whole square form, then y minus c dash by 2 gives you y square minus 2y c dash by 2 gives you c dash y plus c dash square by 4. That's why we have written one more c dash square by 4 on the right hand side. So this equation is something like x minus 0 whole square plus y minus c dash by 2 whole square is equal to c dash by 2 whole square. So this is what you have here. Okay, so this is the case. So this is the case. So first thing, this is of the form x minus h whole square plus y minus k whole square is equal to some radius square. So that represents a circle. So this represents family of circles, means because c dash is constant, you can keep whatever the value you want in place of c dash. So this represents family of circles with now if you see, the center of this combination is 0 comma c dash by 2 and radius is also c dash by 2. Correct? Because the general equation of a circle is x minus h whole square plus y minus k whole square is equal to r square. Okay, so that's why this is the center and radius. Now here if you observe one thing, look, let us suppose if you plot some x and y axis, origin x minus x, y and minus y, for example. Okay, so this is minus y. Now whenever this x minus x, y and minus y, look, center is 0 comma c dash by 2. What is the meaning of the x coordinate 0? Means the center is on which axis? X coordinate is actually 0, correct, for the center. Then center is on which axis actually? Let us suppose the center is on y axis somewhere here, means for one particular value of c dash. Now try to tell me one thing. if this center is c dash by 2, this height is also c dash by 2, correct? Means if this center is 0 comma c dash by 2, this height is c dash by 2. Now what about the radius of the circle? That's also c dash by 2, which means can I say the circles what I draw will have center on y-axis and also they just touch the x-axis. They actually have the center on y-axis and also they touch the x-axis. Can I say this? Because radius and this height both are same. Okay, so therefore these are family of circles with center on y-axis and tangential to x-axis. Means x-axis acts as common tangent. Okay, and tangential to x-axis. Okay, so now if you keep these circles, these streamlines, like this, you have a lot of circles. Similarly, for negative values of c dash by 2, if c dash can be arbitrary constant, so it can be anything. So if this is origin, then your circles are again something like this. So you can see this is how you have the streamlines. Okay, so all these are the streamlines actually here. So all these are the streamlines in this case. Okay, so these are actually the streamlines. So these are streamlines in this case. All these cases basically, if you see, all these are streamlines actually. Streamlines. So that's how streamlines are actually this circles in such a way that their centers are actually on y-axis and they are tangential to x-axis. Okay, so this is how you get the streamlines in case of a doublet. Okay, and basically the source and sink are somewhere here, for example here and here. Okay, so that's how we have the streamlines. Clear? So practically there cannot be any flow that can enter this. So some part of the fluid gets stuck in this particular locations. Okay, whichever is the shaded. For example, if you see, since fluid cannot cut this region because there is some flow, fluid actually remains in this circles actually. Okay, so the fluid which is actually we can move, basically let us suppose if the source is of some length, then fluid flows within this particular area which is available. Okay, it cannot cut the streamlines actually. So these are the streamlines which are actually tangential to x-axis and having the centers on y-axis. Okay, so this equation, this polar equation is actually this. Okay, so this is the case, sin theta by r is equal to c2. And if normally if you might know here itself, I might have shown you r is equal to 1 by sin theta will actually give you some means basically r is equal to some constant into sin theta will give you some circle actually. Okay, so let me show you that graph calculator, polar graph plot. Yes, this is what I think we have seen. So open Omnia. Yes, correct. So here if you see, then we, for example, this small r is equal to some sin theta by c2. So 1 by c2 is some constant. For example, say 2 sin theta, 2 sin theta. Okay, then if you plot this, you will get a circle something like this. Okay, so here if you see, this is a circle which is tangential to x-axis. I hope you can see this. So this is a circle tangential to x-axis. Since I have taken c as 2, center is at this location 1. Okay, so same thing we have done for different values of c2, we get different circles like that. Okay, but always the center lies on the y-axis and this like they actually touch the x-axis. Okay, and similarly here equipotential lines, if you draw, they are again the circles. Look, I am erasing this shaded part and all. Basic idea is to tell you that these are streamlines. Okay, so whatever in blue color, they are streamlines, and whatever are in red colors, this orange colors, if you see, all these will be equipotential lines here. Okay, so these red lines, these orange circles will be equipotential curves actually. Okay, fine. So they are equipotential lines actually. So this is how we have the flow net actually. Okay, so these are the equipotential lines and these are the streamlines. Okay, whatever is in blue color, they are streamlines, and whatever are in this orange color, they are equipotential lines. Equipotential lines. Same thing if you do, like for example, if you again take this along equipotential lines, this is equal to constant, then after this conversion you will get x minus c dash by 2 whole square plus y square is equal to c dash by 2 whole square. Okay, the centers will be on x axis and y axis will act as tangent. Okay, and at this point of intersection, if you draw two tangents at these locations, for example, you take any section, you take a tangent here, and also you take a tangent here, and also you take some other tangent here, then they two actually intersect orthogonally. Okay, so they cut orthogonally each other. Okay, so this angle at any intersection, this angle will be always 90 degrees. Okay, so that's how you have this equipotential lines and also the streamlines. Clear? You know, these equations represent actually circles. Okay, because I have worked a lot of time with these equations in polar form, r equal to 2 sin theta, 3 sin theta, all these things. Okay, so that's how I know that whenever r is equal to some constant into sin theta, circle will have center on y axis and tangent to x axis. Okay, similarly, if r is equal to something, some constant into cos theta, then in such case circle will have center on x axis and tangent to y axis. Clear? This is simple thing that we know because I have done this many times. So intuitively I know that if r is equal to some constant into sin theta, circle will have center on y axis and x axis is tangent. If r is equal to some constant into cos theta, then definitely center will be on x axis and y axis is the tangent. Okay, that's how. Don't get afraid by looking at this diagram. You know how to draw this now. Normally in textbooks you find this diagram and you feel that potential flow is very difficult because this diagram is a bit complicated actually. Okay, but now you know how the diagram came by easy understanding of some 11th class geometry. After 2 attempts you will also know, if you see r is equal to some constant into cos theta, that's a circle with x axis as center, with center on x axis. Okay, and tangent to y axis. Clear? So this is about the story of doublet anyhow. Okay, so these are the streamlines here. So streamlines are, these are streamlines actually. We have taken this for the stream function equal to constant, so we got this equation. Okay, so streamlines are these lines and these orange lines are basically the equipotential lines. Okay, now let us see the vortex flows and circulations actually. Okay, now vortex flows we have seen previously in differential analysis of fluid systems. We have done certain analysis on pressure and all these things. Okay, so let us try to see. For example, let us suppose you have some coordinate system. So let us suppose this is x minus x, y and minus y. Okay, so this is y and minus y. Now if you see, for example, vortex flows, let us suppose if particles are evolving about circular paths. Okay, particles are rotating, evolving in some circular paths. Okay, let us see. Fine. Okay, so let us suppose if particles in this vortex flows are evolving in this particular direction. Okay, for example, there are some particles, fluid particles, which are evolving about this center. Okay, it's a vortex about this point. Oh, now try to understand this. This is a vortex. Normally we take clockwise as the positive sense. Now if you see this vortex flows, so please tell me, in case of vortex flows, in case of vortex flows, of course we are talking about the free vortex. Okay, so in case of vortex flows, now if you see at any location, this is a free vortex, for example. Okay, so we are talking about the free vortex flows. Similarly, at any section, okay, you have the flow of this particular particles like this in different directions. Okay, similarly you have some particles which are evolving. Now, if you see, if you write UR and U theta values for in case of vertex flows, UR and U theta, first thing, no, correct? So that's why U radial is 0. And what about U theta? Since I told this is a free vertex, this is a free vertex. We have seen in case of free vertex in our differential analysis, this U theta is equal to some C by R. Yes or no? Correct? U theta is basically C by small r, we have seen. But because in case of free vertex, as the radius from the center means basically from the hole increases, from the eye increases, the velocity of the particles will be slow actually. Okay, so we know that. Now tell me, why can't I use, means intentionally I'm writing only for free vertex. If you see the case of forced vertex flows are rotational. Okay, angular velocity of the particles is not 0. Okay, then the flow cannot be irrotational. Okay, forced vertex is actually a rotational flow, but in potential flows we define the velocity potential function which can exist only and only when the flow is irrotational. Okay, so only free vertices are irrotational but not forced vertexes. That's why we write the potential flow or the ideal flow analysis only for the free vertexes, because in some interviews they ask you, okay, normally if you write engineering services or something like that, they can ask you, you can write if you want free vertex flow and circulation anyhow. Okay, basically you can understand if I write only vertex flow, that I mean free vertex flows. Okay, so this is a free vertex. Now U theta is equal to C by R. Now therefore if you write F dash of Z, okay, first of all before doing the analysis I'll give you the function. F of Z is equal to minus I times of C into log Z to the base E is what you will get. Okay, so let us suppose if the point, if the center of the vertex is at origin, for example. Okay, if center of vertex is at some other point, Z minus Z naught will come as usual, but let us suppose this is the case. Okay, what is the value of this constant? We will see shortly. Okay, we will define one more concept which is called circulation, then we will see what is that constant. So F dash of Z is equal to UR minus I times of U theta into e power minus I theta. Correct? So this is what you have. So what is UR? 0 minus I times of C by R into e power minus I theta. Now if you want to differentiate this, I mean if you want to integrate this, apply Milne-Thomson method. Applying Milne-Thomson method, then if you apply Milne-Thomson method, we get replace R by Z and theta by 0. Okay, so when you replace theta by 0, this quantity turns out to be 1 actually. Okay, so when you put theta equal to 0, this quantity is 1 and this small r is Z. Therefore F dash of Z is equal to minus I times of C by Z. Correct? So this is what you have, minus I times of C by Z actually. Okay, now if you multiply dz on both sides and if you integrate, if you perform the integration, you have F of Z is equal to minus I times C into log Z to the base E is what you get here. Okay, so this is what the same function I have given you in the beginning, minus I times of C into log Z to the base E. Okay, so this is the potential function, velocity, I mean the complex potential function. Now if you split this, for example, if you split this, because I want to show you what are equipotential lines and what are streamlines actually in this case, this implies F of Z is equal to minus IC times of log Z to the base E. If you expand, half log x square plus y square to the base E plus I times of tan inverse y by x. Okay, so this is what you have. So if you write real parts and imaginary parts, then you can see this minus IC. Look, this minus I, if you multiply here, this part becomes the imaginary part, correct? And if you multiply this minus I to this plus I, imaginary terms go out and we get the real term. So minus I C into plus I, minus I into plus I is minus I square is minus 1, so minus 1 into minus 1, it is plus. So C times tan inverse y by x plus, or generally plus, then this is I times of minus C by 2 times log x square plus y square to the base E is what you have here. Okay, so this is the case. So you have split this into real part and also imaginary part. So you know the real part in this complex potential function is the velocity potential, and this guy is the stream function. Okay, so now if you see, then if you try to plot this equation and this equation, we have plotted already in case of this source and sink concepts. So you got the same thing. So this psi is equal to constant. So if you see along streamlines, psi is actually some constant value. Okay, so along the streamlines psi is equal to constant. So this implies minus c by 2 log x square plus y square to the base e is equal to some arbitrary constant. So this implies x square plus y square is equal to some root c1 or c2, for example, whatever, after deleting this minus c by 2, applying exponential. If you see, this is what you will get. Okay, so x square plus y square is equal to square root of c2 whole square. So these are circles with center at origin, correct? So these are the streamlines actually. Okay, so therefore what are the lines you have drawn? Actually they are the streamlines of this particular case. So streamlines are actually circles here. Okay, so this is, for example, if anti-clock is what you have taken, then psi is equal to c1, psi is equal to c4, similarly psi equal to c2, c3, c4, all these things. Okay, so this is c2, c3, all these things. Okay, now similarly if you write about the equipotential lines, along equipotential lines, you know, along equipotential lines, phi of x comma y is equal to constant. Okay, so this implies phi of x comma y equal to constant. So c times of tan inverse y by x is equal to some constant, say c3 for example. Then in that case you will get y is equal to some tan of some arbitrary constant into x. So these are lines passing through, straight lines passing through origin. Okay, so these are straight lines passing through origin, correct? So these are straight lines passing through origin. So therefore if you see in this case of vertex flows, what we can use this color maybe. So the streamlines, or generally let us use some other color, blue. What about blue? Blue we have used already, so fine. Orange only let us take. So if you see, oh no, it's not looking good. So white color let us take for example. So this anyhow, if you see, this is also one streamline, I mean the one equipotential line. All these are equipotential lines in this case. Okay, so all these are basically equipotential lines. Okay, so this is phi is equal to c1, phi equal to c2, phi equal to c3, phi equal to c4, similarly and so on, phi equal to c8, like this. Okay, so we have the equipotential lines in this particular manner and the streamlines as circles in this case. Okay, so flow cannot cross the streamlines, so obviously the particles which are here will just evolve like this, but they don't go out of this out of this cycle, out of any cycle, so they don't cut the streamlines actually. Okay, so streamlines are the concentric circles that you have, and this equipotential lines are the radial lines that you see here. Okay, now if you see, like in case of source and sink, we have defined something called strength of a source or strength of a sink. Okay, similarly if you have a vertex, what is the strength or what is the power that, or what is the effective or what is the quantity that tells you how effective is the vertex flow. Okay, so if you see strength of a vertex, strength of a vertex okay, so strength of a vertex. Now if you see strength of a vertex, for example, so the strength of a vertex is given by, obviously if these particles rotate effectively with higher velocities and all, means if the angular velocity of the particles is actually high, then in that case, you know, the vortex is generally very effective. And if the particles are moving very slowly in this particular vortex, then the vortex is not much, you know, rotational. So that's why what we do is we talk about the strength of the vortex in terms of its circulation. One quantity that we define is called circulation. It's associated circulation. Okay, so what is this circulation? That's what you have to do. Look, circulation is nothing but, let us suppose along some length, if you take, means let us suppose if there is some flow, then along certain length, what is the effect of velocity on that particular area? Means, for example, see here, we'll see circulation. So what is circulation is basically, look, let us suppose you have some length, for example, say, so let us suppose this is some area and this length is dl, for example, okay, or this length is l, let us say. Now if you take some small length of dl, okay, so let us suppose you take some small length of dl in this case, then the velocity of these particles is present here, okay. So the velocity of the particles is in some direction, v bar, for example. Then let us suppose to this small length that we have chosen, let us suppose the normal to this small length is in some different direction, okay. So let us suppose the normal to this is in some different direction, which is n bar actually, okay. So this is n bar. Now whenever the velocity is high, then the rotation of this element will also be high, yes or no? Means basically, if this velocity is high, the momentum of this fluid will try to rotate this element actually, okay. So therefore this circulation is actually denoted with the symbol which is given here. So this is the symbol for the circulation. So circulation is actually given by integral over the complete area or the complete length or the complete curve. See, v bar dot dl bar is what you have here, okay. So the effect of this v on this small element means basically what happens whenever the fluid is trying to move effectively, then because of the motion of the fluid, this element which is here, this dl or this dl length of element, this will try to rotate actually, okay. So that's why this circulation is actually integral over c or the complete closed path. Let us suppose if you take the total length whichever is here, then the total length v bar dot dl bar, and dl bar can be written as cyclic integral over c v bar dot n cap dl, okay. So whenever you see we write lengths and areas in terms of unit vectors, so n cap dot dl. So this is the value of the circulation, and this is gamma, normal gamma function that you see. So gamma is equal to cyclic integral over c v bar dot n cap dl is the circulation that actually takes place. Now if you see, for example, a 2D element, let me explain you. So let us suppose you have, for example, in a 2D system, x and y coordinate system, for example, okay. So let us suppose you have x and y coordinate system. Now normally in case of differential analysis of fluid flow, I have given you one particular topic which is called translation, deformation and rotation, correct? You might have learned this, okay. Whenever a fluid body has to rotate, then the velocity should vary according to some other function. Means basically, if you see, for example, let us suppose if you take some small block, okay. So let us suppose if there is some small block, this is of length dx and say this is of length dy, for example, okay. So whenever this is of length dx and dy, and let us suppose the velocities are a, b, c, d, for example, then the rotation of this element will take place if u is function of y and v is function of x, correct? So normally what we have taken at that time is u is function of both x comma y and v is function of both x comma y. Then the rotation of the element, of course the deformation is due to dependence of u on x and dependence of v on y, but the rotation of the elements is due to dependence of this u on y. Means what happens if these two are not at same velocity, then definitely what happens, they will try to deform actually, correct? So we have seen the rotation is due to dependence of u with respect to y and dependence of v with respect to x, correct? Now let us suppose, for example, let us suppose this layer is moving with a velocity u in this case, then the velocity of this layer is given by some other value. See, for example, if this is u, if this layer AB velocity is u, this velocity which is at a height of dy is given by u plus dou u by dou y into dy, correct? So this is what you have. Yes or no? Because whenever u is depending on y, the two layers are separated by a gap of dy, then in that case, if the bottom layer velocity is u, then the top layer velocity is u plus dou u by dou y into dy actually, okay? Similarly, if this velocity is v, if this velocity is v, then this velocity here is equal to, so if this velocity is v, then this velocity is v plus dou v by dou x, because these two layers are separated by a amount of dx, so dou v by dou x into dx actually here, correct? So that's what you have, v plus dou v by dou x into dx. Now let us suppose these velocities are trying to rotate this block. This velocity means the velocity of AB and BC are trying to rotate the block in anti-clockwise direction, and the velocity of this AD and velocity of this CD are trying to rotate this block in the clockwise direction. So let us suppose if we take clockwise is negative and counterclockwise is positive, like always. So taking counterclockwise as positive, taking counterclockwise as positive. Now see here carefully, you need cyclic integral over the complete path C. Let us suppose this is complete path C, v bar dot dl bar actually in this case, okay? Now here in all cases you see that dl and v both are actually parallel to each other, okay? So that's why this is angle between them is 0, so dot product is nothing but product of individual elements. So this is equal to, look, if we want, for example, if you take this element, it's a closed element. If you want this integration or the complete closed path C, that you can split into 4 parts. Integral AB v bar dot dl bar plus integral BC v bar dot dl bar plus integral CD v bar dot dl bar plus integral DA v bar dot dl bar, okay? So this is what you have. So normally if you want to evaluate this integration or the complete closed path, rather than doing it on the complete closed path at a single go, we have actually split this into 4 parts, AB, BC, CD and DA, okay? So that's how we have taken this. Now on AB, first of all, if you see on AB, look, on the total length, integration or AB means this total length, we know that at any point the velocity of this layer is u. This layer is moving with uniform velocity, u is depending only on y, for example, let us say. Then in such case, this v bar dot AB is nothing but this dl, means this AB and u are parallel to each other, so that's why the dot product is nothing but product of their magnitudes, correct? Now one more thing, this u is trying to rotate this block in the anti-clockwise direction, because this effect moment about this is nothing but this is in the anti-clockwise sense, so that's why v into dl is nothing but u into dx in this case, plus on BC this velocity is also trying to rotate this block in the anti-clockwise sense, so v plus dou v by dou x into dx into the length is dy. Next, this c is trying to rotate it in the anti-clockwise sense, so minus u plus dou u by dou y into dy multiplied with length of this element is dx. This velocity is also trying to rotate this clockwise, so minus v times of dy. So these are the expressions that you get here, clear? Because at any location v bar and dl are parallel to each other, so that's why the dot product of those two is nothing but individual magnitudes product, okay? So that's why u into dx and this v into dy, these two are positive because they are trying to rotate this element in the counterclockwise sense, normally taking counterclockwise as positive in our notations, and these two are negative because they are trying to rotate this in the clockwise sense, okay? So now if you simplify this result, u dx and this u into dx gets cancelled. Similarly, this v dy and this v dy gets cancelled actually. So if you try to write something, this is equal to dou v by dou x minus dou u by dou y times dx dy is what you have here. Okay, so dx dy is constant in both the terms, dx dy and dy dx. So this dx dy can be taken out. Okay, so how they are parallel? Because velocity is in this direction, the length of the plate is also in this direction. Okay, the length of the layer is also in this horizontal direction. Clear? They are actually collinear, means basically they are coinciding on each other, so that's why they are parallel. Clear? Basically my intention is to tell you that the angle between them is 0, that's it. Okay, they are actually collinear, no? Length and velocities, they are basically at 0 degrees inclination to each other. Clear? This is what you have. Now I want to ask you one thing. Normally when this element is rotating about some perpendicular plane, let us suppose this is the axis about which it is rotating. Okay, so rotation in the z plane is given by half times of dou v by dou x minus dou u by dou y. Yes or no? Correct? Did we see this? We have seen the component of angular velocity. Normally if you take half times of curl v bar, then this is the component of rotation of this particular element. Yes or no? One thing, in this case dou v by dou x minus dou u by dou y, then here if you see we wrote something called vorticity, which is 2 times of angular velocity, which is nothing but curl of this vector v bar. Correct? So this is what we have seen in differential analysis. So therefore this component which is here can be written as, or this component which is here basically can be written as 2 times of omega z into dx dy is what it can be written. Okay, now 2 times of angular velocity is nothing but curl v, which is known as vorticity vector. This vorticity is given by this omega symbol which we have seen. So this omega symbol, if you see, this omega z into dx dy. So therefore circulation, so see here, circulation in bracket, this symbol of circulation gamma is equal to this 2, this is the circulation what we have taken totally. So 2 times of omega z is nothing but the component of vorticity in the z direction multiplied with dx dy is nothing but area of the element. So this is nothing but area of the element. Okay, so therefore circulation is actually equal to, circulation is equal to vorticity into area of element. Area of element. Okay, so this is what we have, or generally vorticity is equal to circulation divided by area. So this is the common relation between circulation and vorticity actually here. Okay, so this circulation talks about the effect of velocities to rotate the element. Okay, so that's why this vertex flows are actually, the strength of this vertex is determined by the capability of these velocities to actually rotate the flow. Okay, so therefore if you see in this case, so vorticity into area of element actually. Okay, so therefore circulation is vorticity into area of the element is what you have here. Okay, now what about that constant c we have seen? So this constant c, whatever you have here. Okay, so this constant c is written as, look, at any given section, for example, the strength of the vertex which is given by its circulation, which is vorticity into area of the element actually. Okay, so vorticity into area of the element. So therefore now strength of the vertex, strength of the vertex actually is equal to, strength of the vertex is equal to associated circulation. So whatever is the circulation that's present in this case, so this is associated circulation. So this is equal to, in this case, dou associated circulation. So basically if you see, this is dou v by dou x. So here we have seen dou v by dou x, right? So we have seen this is c by r actually. Okay, u r is 0 and u theta is c by r. Okay, so if you write omega z, then this omega z value we have seen already. At any radius, at any given radius, at any given radius, okay, So at any given radius, for example, let us say at some radius, for example, something like this. So let us see at some radius, unit length of the rotation, this area available is 2 pi r into 1. Okay, and what about the vorticity? So we can write this as circulation is equal to 2 pi r into this velocity, which is here, which is u theta. Okay, because u theta is the rotational component of velocity, so u theta, and this is given by this circulation actually here. Okay, so this is circulation. Now this circulation is equal to 2 pi r times this u theta at any location is given by c by r actually. So if you cancel this r and this capital R, this c which is here is given by circulation divided by 2 pi. Okay, so this is the value of the constant c. Like in case of source, or in case of strength of source and sink, we have m by 2 pi. Similarly here, this circulation divided by 2 pi is what you have here. Okay, because this u theta, the velocity, or basically if you see, the vorticity is given by the angular velocity, and v theta is nothing but the velocity which is angular. Okay, so v theta is nothing but angular velocity of the particles at any given location. So the vorticity is given by this angular velocity, which is c by r, multiplied with the area. We are putting r equal to 1 actually. I mean the length of the vertex is basically equal to 1, so that's why this r gets cancelled, and c is equal to circulation by 2 pi. Okay, so whatever is the vorticity here, that is actually equal to the angular velocity u theta directly here. Okay, because u theta talks about the angular velocity of the particles, and this is 2 pi r into u theta is what you have here. Okay, so this is the constant c. Therefore for a vertex of strength or generally of circulation, for a vertex of circulation gamma at the location z is equal to z0. Okay, so at the location z is equal to z0 is given by okay, so this value is given by z is equal to z0 is given by so what is this value? This is given by f of z is equal to, at location z is equal to z0, the complex potential function is given by the complex potential function is given by f of z is equal to minus I times circulation by 2 pi into log z minus z0 to the base e. Okay, so this is the velocity, I mean the complex potential function. In this case, f of z is equal to minus I times circulation by 2 pi into log z minus z0 to the base e. If the if the vertex is at origin, then this z0 is actually 0 in this case. Okay, so the strength of the vertex is given by its circulation quantity. Clear? Like things are very much similar to the concept of source. That's it. Okay, so how we have the concept of source and sink, similarly the case of vertex flow is here, and the strength of the vertex is given by its circulation actually. Okay, so these are the basic flows that we talk about. Okay, so we talked about the uniform flow in x direction, uniform flow in y direction, uniform flow inclined at some angle, then flow in sectors. We have seen for n equal to 1, n equal to 2, n equal to 3, n equal to minus half, it is like flow past a sharp edge, n equal to minus 1, it's a doublet. We have seen these things. Then we talked about the concepts of source and sink. Then again we have understood the meaning of doublet and the complex potential function derivation, and then we thought of this vertex flows and concept of circulation. Clear? So these are the basic flows. Now normally if you see, we have written this values omega z is equal to dou vr by dou r minus 1 by r times of dou v theta by dou theta, all these things actually, if you remember, dou v theta by dou r, and this is dou vr by dou theta, all these things. So from that analysis you will get that. Okay, I'm not doing that derivation again because some solving of partial things to be there adjustment, so I'm directly giving you the value. Okay, normally if you see the expression for rotation and all, if you remember, we got one expression for the rotation. Okay, there if you take out vr equal to 0 and if you write dou v theta by dr as all these things, then you will get that. Okay, so I'm not giving this directly, I'm writing u theta. So superposition of flows. So like basically we will try to superimpose different flows and we'll try to understand the situations again here. Okay, so the first superposition here that we do is superposition of uniform flow with source, with a source. Superposition of uniform flow with a source. Okay, so how do we superimpose? So basically we know that uniform flow is having some velocity in this x direction, for example, of course in the x direction. Okay, uniform flow in this direction. So this is how you have here. So this is coming at some velocity u, for example. Okay, so this is coming at some phase time velocity u plus horizon x minus. Okay, so basically if you see, for example, if there is one point here, okay, then so let us suppose there is some point, so from that point you have flow in all the directions. Okay, so you have a source like this from which there is some fluid flow. Okay, so they are the vertex flows. Okay, so this is source and this is actually uniform flow. Okay, so uniform flow and source. So when you combine this, what can be the situation actually? Okay, so that's what we need. So first of all, if you write f of z for this, then you know just complex functions can be just added straight away. So this is a uniform flow along x direction, so uz plus this is a source of strength m, for example, source of strength m, let us say, source of strength m placed at origin, so m by 2 pi ln z. So this is the complex potential function for this flow. Okay, uz is due to this uniform flow plus this m by 2 pi ln z is due to this source actually. Okay, so this is the complex potential function. So in this case we have f of z is equal to uz plus m by 2 pi into ln z actually here. Okay, now if you split this into r into e power I theta form, for example, then you have u into r e power I theta plus m by 2 pi times of this ln z. Okay, so ln z actually, if you see, m by 2 pi ln z can be written as half times, or generally you can write directly as ln r plus I times of tan inverse y by x, correct? So this is what you have. Okay, generally I theta, you can write theta for example, instead of writing tan inverse y by x and all, let us write theta. You know this I times of theta. Okay, so this is what you have. So if you split and write the common real part and imaginary part, u r times of cos theta plus I sin theta plus m by 2 pi times of ln r plus I times of theta, correct? So this is what you have if you expand it slightly. Okay, because this z can be written as r into e power I theta. So in yesterday's class I have shown you how this comes, and this e power I theta can be expanded like this. So if you club the real part and imaginary part, then you have u r cos theta plus m by 2 pi ln r, m by 2 pi ln r. So this is the case, plus I times of u r sin theta plus m theta by 2 pi is what you have here. Okay, so this is m theta by 2 pi. Now if you see, this can be, this function got split into some real part plus I times of imaginary part. So therefore this value is phi, or the stream function, this velocity potential function, and this is the stream function in this case. Okay, you have to do this analysis little carefully, because missing of some I or missing of plus or minus signs can, you know, change the results. That's why if you see, this is the velocity potential function and this is the stream function for this case. Okay, therefore phi of r comma theta, phi of r comma theta is equal to u r cos theta plus m by 2 pi times ln r is what you have. Okay, similarly this stream function of r comma theta is equal to u r times sin theta plus, okay, m theta by 2 pi is what you have here, m theta by 2 pi. Okay, so this is m theta by 2 pi. Similarly, if you look at the velocities, we have f of z is equal to u plus, okay, uz plus m by 2 pi ln z is what you have here. Okay, so therefore if you differentiate this, f dash of z is equal to u plus m by 2 pi into differentiation of ln z is 1 by z, correct? So we have 1 by z actually here. Now try to understand one thing. If you observe carefully, look, I told you already magnitude of this f dash of z, because this is some complex number. So if you calculate magnitude of this complex number, this is equal to the magnitude of velocity at that point. Yes or no? Correct? Because obviously f dash of z can be written as u minus iv, or maybe u r minus I times of u theta. So if you calculate the magnitude of that complex number, you will get either u square plus v square square root, or square root of u r square plus u theta square, correct? So if you calculate this magnitude of f dash of z, means basically if you calculate the magnitude of this complex number, then we have a this velocity. Okay, now we know that we have some stagnation points. Okay, so stagnation point, stagnation point. So what is stagnation point? We have seen in case of pitot tubes, all these things, the point where the local velocity of the flow is 0, correct? So the point where the local velocity of the flow, the point where the local velocity of the flow is 0, correct? So the point where the local velocity of the flow is 0. So in this case, if you want to observe stagnation point, look, try to understand this. Normally you have f dash of z is equal to u minus iv, or maybe if you convert to polar, u r minus I u theta e power minus I theta, correct? Now magnitude of the velocity is nothing but u square plus v square square root, or this is also equal to square root of u r square plus u theta square. We can see anything. Now if this magnitude of velocity has to be 0, then definitely this quantity has to be 0 and this quantity has to be 0. Yes or no? Means similarly here, this quantity should be 0, and this individually both u and u theta should be 0, and also u and v should be zeros in this case. Okay, so therefore magnitude of velocity is 0 only when both the components of velocity is 0. Now therefore if both u and v are zeros here, if both u and v are zeros, what is the value of this f dash of z? 0. Similarly here, if these two are zeros, then this f dash of z is 0. Means one thing I want to tell you, if there is some stagnation point, the stagnation point comes at the location where f dash of z is 0. Yes or no? That means basically highlight a statement here. For a point z0 to be a stagnation point in a flow, a stagnation point in a flow, f dash of z at z is equal to z0, this should be definitely 0. Yes or no? For magnitude of velocity to be 0, individually this u and v both should be 0. Similarly u r and u theta should also be zeros actually. Okay, so whenever they are zeros, then definitely this f dash of z will also be 0. Okay, so this is simple understanding. Now if you see this, so therefore first stagnation point, f dash of z is equal to 0. This implies u plus m by 2 pi z is equal to 0. So z is equal to, so from this equation, minus 2 pi u by m is what you have here. Okay, so this is the complex number, this is the location at which you have your z is actually 0, and this is basically on the real axis, means on the real axis. Okay, so because if you see, we have u plus m by 2 pi z is equal to 0. So from this equation, if you simplify for z, u is equal to, sorry, 2 pi, u is equal to minus m, u is equal to minus m. Just a minute, I think this equation is correct. So m by 2 pi z, m by 2 pi z is equal to minus u. So z is equal to minus m by 2 pi u. I think this is correct now. Okay, so this is the correct location. Okay, so z is equal to minus m by 2 pi u is the location at which you have the stagnation point. Means this is the point. Means if you solve this, this is a real number, of course, because strength is a real number, velocity is a real number, 2 pi is constant. Okay, so you will have z is equal to minus 2 pi u is the location of the stagnation point. Okay, means one thing is clear, since this is real, this is a real, stagnation point lies on x-axis. Stagnation point lies on x-axis actually. Okay, so stagnation point lies on x-axis. Now, so this is one stagnation point for this particular situation. Okay, now let us try to see how the streamlines actually look like. Okay, so if you see, so stream functions, so stream function is given by u r sin theta plus m theta by 2 pi. Okay, so we have given, or generally we have psi of r comma theta. So stream function in terms of r comma theta is given by, at any location it is given by u r sin theta plus m theta by 2 pi. U r sin theta plus m theta by 2 pi is what you have here. Okay, now if you see, so let us take for example x and y coordinate systems, which is generally the polar coordinate case also. X y minus x minus y. Okay, so we have this. Now if you see, guys, look, this is very important, so please listen carefully. Along a streamline, psi is constant, correct? We know that along a streamline, along a streamline, psi is equal to constant. Correct? So let us take one particular value of stream function. If psi is equal to m by 2, because there is some m by 2 here, so I want to write something in terms of m by 2. So if psi is equal to m by 2, this implies m by 2 is equal to this function u r sine theta plus m theta by 2 pi. Okay, so if you write expression for r from this equation, this implies u r sine theta is equal to m by 2 into 1 minus theta by pi actually here. Okay, so this is what you have. So this implies r is equal to m by 2u times m by 2u times this, if you take LCM, pi minus theta by pi into this sine theta is also here, into this sine theta is also here. So pi, if you write outside, small r is equal to m by 2 pi u times of m by 2 pi u times of pi minus theta by sine theta, pi minus theta by sine theta is what you have here. Okay, so this is the graph of the streamline actually. Correct? So at psi is equal to m by 2, this is what you get. Yes or no? Because if you simplify this carefully, m by 2 is equal, u r sine theta is m by 2 minus m theta by 2 pi. Okay, so therefore r is equal to m by 2u, if you write here, pi if you take out, pi minus theta by sine theta. So this is what you have here. Okay, now if you plot this graph, for example, because if you take, this is theta and radius direction, if you plot this graph on a r versus theta plane, the same coordinate plane in polar coordinates, if you plot, you will get the graph in this way, that which I am going to draw now. You will get the graph then it almost becomes flat, and similarly, look, let me draw some sharply. Then this becomes flat almost. Okay, so after increasing to some extent, it becomes flat almost like this. Okay, similarly here also, it slowly increases and it becomes almost like flat after some time. Okay, so it slowly increases and it becomes flat. Now this is how the shape of the streamline comes out. Means if you plot this equation r with theta, this is how we will get the shape. Okay, so this is at psi is equal to m by 2. Now I'll show you this using that plotter which we have seen. So let us suppose this is some constant value, u is constant, m is constant. So let us suppose this is some constant value, for example 5, something like that. So let us try to plot this. So if you plot this, r is equal to some constant 5 into, for example, 5 times of pi minus theta. So pi minus theta divided by sine theta. Okay, so sine theta. So if you plot this function, look, this is how the shape of the function comes out actually. Okay, so if you see carefully here, this is at some far, okay, 5 is very large value. For example, let us take 1 in this case. Okay, so 1 into pi minus theta, pi minus theta, okay, by sine theta divided by sine theta. Okay, so if you plot this, for example, now you can see the graph is actually something like this. Okay, so different values you have, but initially if you take the shape of this curve, for example, theta is from 0 to 2 pi is what I think it has taken. So let us, so main intention is to show you this part of the graph. Okay, so if you see this part of the graph, slowly this value increases actually. Okay, and after some large length, what happens, you see here, this is almost like a straight line. You see x is rapidly, look, this is 5 actually. Okay, but this line is not exceeding 5. Whatever the time you take, this became almost some constant. Okay, so this is what I want to show here. You will actually get the shape of the graph something like this. Okay, so let me draw a little neatly because I think it is not very good. Okay, so this is how you have the graph normally. Now, if you see this case, this is actually some streamline, correct? Yes or no? Because psi, this is one particular streamline when m, this psi value is equal to m by 2. So practically speaking, flow cannot enter this streamline. Yes or no? Means whatever is the flow that's moving out, that flow cannot enter this particular streamline. Yes or no? Because flow cannot cut the streamline. So if at psi equal to m by 2, means whenever you have this r in the form of some constant into pi minus theta by sin theta, if this is the streamline, then practically speaking, flow cannot enter this streamline from outside. Okay, so therefore you assume this as, so whatever the flow is coming, that should move only out, and the flow cannot enter this, cut this streamline. Okay, so when flow cannot cut this streamline, this part which is here, this is which is here actually. So this is treated as a solid body. Okay, because if you see, flow cannot enter the streamline, so whatever is the region here, this region is actually considered as a solid body with this particular boundary. Okay, but at the same time you can see these two ends meeting, but can you see these two ends meeting at some point? Can you see these two ends meeting at any point? Because they are maintaining some constant thing. Okay, so that's why you cannot see these two ends actually meeting each other. Okay, so that's why this body which is assumed here is assumed as half body, because it's like only, let us suppose if you take some long body and if you cut into half, then this is only half body that you have here. Okay, so this case is called flow over or flow past a Rankine half body. This analysis was given by Rankine, so Rankine half body actually. Okay, so this is flow over or flow past a Rankine half body, and normally we use this analysis for analyzing flow past some submarines and all. Okay, because comparatively the length of the submarine will be very large. Okay, but initially this will be the nose of the submarine and all, so that's why examples, flow over submarine if you take for example. Okay, so flow over submarine, flow over submarine. Clear? So is this clear to all of you? Did you understand why I am calling this half body first of all, and then why this situation can be analyzed for flow over submarines? Because submarine's length will be very large and the nose will be very small actually as compared to the length of the submarine. Okay, so that's why these situations are used for analyzing flow over submarines. Clear? And why this is called flow past half body? Because practically fluid cannot enter this, so this is taken as some solid boundary and this is taken as some solid, so that's why this can be taken as flow past a solid, but this is only half, so that's why it's called half body actually. Okay, clear? So now if you see here, there are certain things which are of importance. Okay, some geometrical things. What are they? Look, let us see here. What is this length? Means basically if you take for example O, for example A, this is origin O, B, C, okay, D and E. For example, after this they are constants. Okay, the line lengths are constants. Let us suppose if these are the constants, if these are points, we are interested in some distances. Okay, OA, what is OB? Of course, situation is symmetric, so if you know OB, you know total BC. Similarly, if you know what is this length D, then definitely you can calculate the total length. Okay, now let us see one thing. Let us see here. So now theta is at any location, means for example if you join these 2 points, then this is theta at some location. Okay, so this is theta. Okay, now let us see OA. First of all, the geometry of that curve is given by at psi is equal to m by 2. The geometry of that curve is given by radius, means basically what is radius from this point, what is the distance is the radius correspondingly. Okay, so at this point psi is equal to m by 2, r value is equal to given by m by 2 pi u times pi minus theta by sine theta. Okay, now please tell me one thing. Initially, if this is the horizontal line, theta is equal to 0. Now, if you want to calculate this distance, I have to calculate my r at theta equal to pi. Yes or no? Because you see this point, if you see, OA is making an angle of 180 degrees actually with this horizontal, because this is in reverse condition. So whenever this is in reverse condition, then this OA is actually equal to the value of radius when theta is equal to pi. Correct? Can I say this? Yes or no? Because at any point on this complex plane is denoted by two values, radius and theta. Okay, so r comma theta. So if I want this length, that means I have to calculate this r when theta is equal to pi. Yes or no? Because in polar coordinates, any point in a plane can be focused by two things, radius from the horizon and also the angle of inclination theta. So here, when angle of inclination is 180, the point is at a radius r. So if you want this smaller, you have to calculate the value of smaller at theta is equal to pi. Correct? So therefore, if you see first case at theta equal to pi, at theta equal to pi, what is the value of r, which is OA, is how much? Okay, so let us see this. Limit theta tends to pi, small r is equal to limit theta tends to pi m by 2 pi u times of pi minus theta by sine theta. Now, this m by 2 pi u is constant. It has nothing to do with this theta. 2 pi is constant, strength of the source is constant, the velocity of the uniform flow is also constant. So m by 2 pi u you can take outside the limit. M by 2 pi u times of limit theta tends to pi, pi minus theta by sine theta is what you have here. Correct? So this is pi minus theta by sine theta. Now please tell me one thing. When you put theta equal to pi, pi minus pi is 0 divided by sine pi is also 0. So you are getting 0 by 0 form. So in limits, when you get 0 by 0 form, what do you do actually? This is 0 by 0 form. So therefore, this can be written as m by 2 pi u times of, now theta tends to pi. So limit theta tends to pi, differentiation of this quantity with respect to theta is derivative of pi is 0 minus derivative of theta with respect to theta is 1 divided by derivative of sine theta is cos theta. Okay, so if you substitute theta equal to pi, this limit will give you a value of 1 actually. Correct? Because theta, when you put theta equal to pi, cos pi is minus 1. So minus 1 by minus 1 gives you 1 actually here. Okay, so this limit is 1. Therefore, at theta equal to pi, at theta equal to pi, radius value, which is OA in this case, is m by 2 pi u. Okay, m by 2 pi u. So this value, whatever it comes here, these things are important. I think last year in 𝐂𝐸 it came, last year or previous year, I don't remember, but it came once. Okay, they can ask you if they want to ask simple things, all these things. Okay, so this value, if you see, this value whichever is here is m by 2 pi u. Now, yeah, differentiate and put 0. So we got this value is m by 2 pi u. So this radius is m by 2 pi u. I want to ask you one thing. Look, we told this case as flow over a cylinder, flow over this half body. So try to understand. Let us suppose if flow is trying to come like this. If flow is trying to come like this and it's getting diverted here, just in front of the nose, just slightly in front of the nose here, if you take a point here, just slightly in front of the nose, if you take a point here where R value is almost same, can you tell me at this point what is the velocity of the fluid? It is coming, and basically here there is a solid, solid obstacle. So please tell me, whenever the particles are coming and if there is some solid obstacle, then at location very close to the solid boundary, what is the velocity of the fluid? At the location which is very close to solid boundary, then because flow is directly coming like this and this is the obstacle that's present here, so what is the velocity at that point? 0, obviously. Correct? the velocity is at that point is 0, because that's actually a, if you see, whenever the flow comes down, then definitely there is some solid blocking, so definitely at that particular location the velocity of the flow is actually 0. And if you observe one more thing that we have done previously, stagnation point is from this f dash of z is equal to 0, m by 2 pi u, and this length is also m by 2 pi u. Okay, so this is the stagnation point in the flow, means just at the edge of the body we have the stagnation point. So that's why if you see, this is actually the stagnation point in this case. Okay, understood how from velocity conditions you have seen? Similarly from geometrical, the stream function curve also you have identified that z is equal to m by 2 pi u is the stagnation point of the particles of the flow in this particular case. Okay, now one more thing, what about here at this location? At this location OB, what is OB? Okay, so case 2 for example, which means not case, second location, at theta equal to pi by 2, because you see this OB is nothing but, when you rotate this line, this R, if you want you have to put theta equal to pi by 2. So at theta equal to pi by 2, what is at theta equal to pi by 2, what is this length R? OB is how much? Let us see. So limit theta tends to pi by 2, what is R value? This is the common expression, so m by 2 pi u times pi minus theta by sin theta. Okay, so this is sin theta, pi minus theta by sin theta. So this value if you calculate actually here, so this implies OB is equal to m by 2 pi u is again constant, m by 2 pi u is constant here. So whenever m by 2 pi u is constant, then this value is m by 2 pi u is constant, then in that case limit theta tends to pi by 2, pi minus theta by sin theta, correct? So we have pi minus theta by sin theta. So OB is equal to m by 2 pi u into, if you put theta is equal to pi by 2, pi minus pi by 2 gives you pi by 2 divided by sin pi by 2 is 1. So this is pi by 2. Okay, so this if you simplify, pi and pi gets cancelled actually here. So this gives you m by 4u actually here. Okay, so this is m by 4u is the value. So therefore OB is equal to, and this OC and OB are same because this is actually symmetric. Okay, so OB and OC are same. So OB equal to OC is equal to m by 4u. This implies the length BC is equal to m by 2 times of u, correct? Because BC is 2 times of OB or maybe 2 times of OC. So that's why m by 2u is what you have here. Okay, so this total length at this location BC value is m by 2 times of u. Clear? So that's how we get the expression. So simple, wherever you want the R value, put the corresponding value of theta. That's it. Okay, you will get the answer easily. Fine. So this is m by 2u is what you have here. Okay, so m by 2u is the correct answer. So basically from this analysis you can easily get that. Okay, so BC is m by 2u. Now I want one more thing actually which I am interested in. Look here, this length is constant, yes or no? Means this height, once you know this height, means for example, let us suppose if you connect these points DE for example, after this point, after this location, this DE length is actually constant, yes or no? Because these two are almost parallel. Okay, so when they are parallel, then it's constant value. Now what is DE? That's what we are interested to know actually. Okay, so how to calculate DE? Let us see one technique. At this location we don't know what is this radius. Okay, we don't know what is this radius, otherwise we would have done sin theta. But you know one thing, I'll ask you one thing, so try to respond here. Okay, here itself we can talk about. See, for example, if you take this point, okay, then you connect this point, then theta in this case, means if you take theta in this case as theta dash, then one thing is very clear, theta dash will be less than theta. Yes or no? Correct? If you take one point here, then and if you connect with radius, then this theta dash will be less than this theta. Can I say theta dash is less than theta? Similarly, let us suppose if I connect another point, then theta dash will be much smaller. So let us suppose if I take at a very large length, what will happen to this theta? So please tell me. Theta will approach to 0. Yes or no? If I take a very large length, for example, let us suppose at some r tends to this length at a takes at very large distance, then the line will actually keep connecting something like this. It will go to some large distance and it will connect. Then this angle theta will almost become 0. Let me tell you one thing. So basically when r tends to infinity, so let us suppose from this point, if r is tending to infinity, then theta tends to 0 actually. Okay, so let us delete all these things. Fine. So we know one thing. Okay, so see here, as r tends to infinity, theta tends to 0. We know this. Okay, now what I can do here is, look, this is some origin maybe. Okay, this is a polar plane, this is origin. So let us suppose you have the curve something like this. In this case, look, let us suppose for example here it got converted to some straight line. Okay, for after this there is no increase in the, after this point there is no increase, after this point there is no increase in the height, means basically whatever is this distance, same is the distance all over. Okay, same, this distance is same. Okay, now try to tell me one thing. If I connect 2 points like this, which are very far actually, okay, this theta is almost 0, it is very far distance, then at this location, if I say this height is for example h, if this height is h, then definitely this height will also be h. Correct? Yes or no? So please type in the chat box. If this height is h, since this height is not changing, this will also be h. But at this point, when this r is very large, this theta is actually very small. Okay, so if theta is very small and if this radius is r, then this h value from this triangle is nothing but r sine theta. Correct? This is what we have. So because from this triangle O, this for example if you take the vertices, for example something like u and or not u, for example x and y, for example, then from this triangle OXY, this height h is nothing but r times of sine theta, and r is very large value. Okay, now and theta is very small actually, almost 0. So therefore at r tends to 0, sorry, at theta tends to 0, h is equal to r sine theta, and this h in our case is actually equal to, in the previous case if you see, dE by 2. So dE by 2 actually, dE by 2, because this h and this dE by 2, if this is d and if this point is E, then h and dE by 2 both are same. Okay, so dE by 2 is equal to limit theta tends to 0 r sine theta, r sine theta. Correct? Because h is r sine theta, but that is the value of r sine theta when theta is very small, so r is 0. So this is equal to limit theta tends to 0. What is smaller? Smaller is m by 2 pi u pi minus theta by sine theta. So this is the value of r into this sine theta is here, so we have one more sine theta. Okay, so we can cancel sine theta here in both the numerator and denominator. Now if you replace theta equal to 0, then this equation gives you m by 2 pi, or sorry 2u is what you have. Pi gets cancelled, because when you put theta equal to 0, this is pi, so pi gets cancelled, so you have m by 2u actually. Okay, so this implies dE is equal to m by u actually here. Okay, so this is m by u is what you have here in this case. Okay, so dE is equal to 2 times of this value. So m by 2 pi u into pi minus theta by sine theta is what you have as the radius and sine theta of that component. So theta gets sine theta gets cancelled, and if you put theta equal to 0, you have m divided by 2u. Okay, so dE by 2. So this length is me by 2u, which is actually equal to the total length in this case. Okay, so m by 2u is means basically if you see in this case, this dimension is m by 2u. M by 2u is what you have here. Okay, so this is m by 2u is what you have here, and at this location, this OB means this distance. If you see, for example, this distance or this total distance BC is again m by 2u, means the length becomes flat, means basically the curve becomes flat after this D. For example, this half length is actually equal to the total length at this point. Okay, so BC is equal to half of this DE, or basically if you keep this point F in this case, if you keep this point F in this case, this FD is nothing but BC value. Okay, because you see BC is also m by 2u that we have calculated here. Clear? So that's how we calculate the radius values at different angles, theta equal to 0, theta equal to pi by 2, and theta equal to pi actually. Clear? And length of the body is very large, infinity. Okay, it's a half body, so you cannot find the other end. Okay, the length of the body is very large actually. Clear? Basically I've just played with some geometry and trigonometry, that's it. Okay, nothing big I have done actually. No more. After you get this expression, then no more fluid mechanics. Everything I have done is little mathematics, that's it. Okay, calculation of some limits and all. Okay, so that's what you have. So this is generally analyzed as the case of flow past a half body. Okay, flow past a half body, and this half body is called Rankine half body actually. Okay, you know why this is called half body? Because you cannot see the other end of the body, and this, since this is a streamline, flow cannot cut this streamline. This is assumed as some solid body actually. Okay, so if you so let us see it from the beginning. So superposition of uniform flow with a source gives you the case of flow past a Rankine half body. Flow past a Rankine half body actually. Okay, so this is flow past a Rankine half body, and this f of z is given by uz plus m by 2 pi ln z is what you have here. And so basically everything you can see, stagnation point first you identified from f dash of z, same thing you identified from the geometry also. Okay, from this calculation of limit, this psi is equal to this, or this length is m by 2 pi u, then this is m by 4u, this is m by 2u, and this total length is m by 2u, this total length is m by u is what you have. Okay, so these calculations are a bit important for you. Okay, so BC value is m by 2u. Last time what they have asked in exam is, as far as I remembered, in 𝐂𝐸 in engineering sciences paper, they have asked, they have given you this function, I think. Okay, not this, maybe they have given in terms of tan inverse y by x something. Okay, they have, instead of this I theta, means basically they have given you this stream function. Okay, yes, correct, they have given you this stream function. Then they asked at psi equal to m by 2, what is this value of BC value they asked. Okay, so stream function they asked. If you know stream function, from the stream function at psi equal to m by 2, means basically how to do this 3-4 lines, whatever is in between. So 3-4 lines, then you put theta equal to pi by 2, that's it, you will get the answer. Okay, so this is what they have asked in the last or maybe before last year, I don't remember exactly, but something like this. Okay, once you know the stream function, you generate expression for r, then calculate at whatever the angle you want. Okay, by putting theta equal to, calculating at that limit. Right, so if you summarize this result, basically in case of this superpositions what we have discussed today, if you summarize the superpositions case, then uniform flow plus source. So this gives you the case of flow past a Rankine half body flow past a Rankine half body flow past a Rankine half body is what you have. So flow past a Rankine half body. Then we have also seen source plus sink. Source plus sink equals tense, equal tense and placed close to each other. And placed close to each other. In this case, you got a doublet actually. Okay, so this is the case of a doublet. Fine. This is the case of a doublet, and normally if you take source and sink, need not be of equal strength and need not be kept close also. In such case, whatever you get is called a Rankine oval. Rankine oval. Okay, look, this normally oval shape, you know the shape of the oval, correct? So what happens is like the elliptical shape, of course. So if you see, in case of doublet, when you done the analysis, the streamlines are concentric circles, correct? But whenever you take concept of source and sink, and if you try to do, we will actually get ellipse. Instead of circle, we will get actually ellipses. That's why it's called a Rankine oval, because m1 and m2 are not equal in that case. Okay, so that's why this is the case of a Rankine oval. Whatever is the condition, we write m1 by 2 pi into ln z minus, let us suppose if this is placed at z equal to z1 and this is placed at z is equal to some other location, say z2. Okay, then in such case we will write this this source as m1 by 2 pi ln z minus z1 minus m2 by 2 pi ln z minus z2. That's the potential function that we write, and from that we will calculate the stream function. Basically, if you split it into real part and imaginary parts, you will get the stream functions. Then if you take, for example, some stream function equal to constant, and if you try to plot, you will get the equations of ellipse. Okay, we got circle equations, we will get the ellipse equations in this case. Okay, so this is the case of Rankine oval. Okay, and these are the three superpositions that we discussed today. Now there are two more important superpositions which maybe we will discuss in the next session. These two superpositions are, first thing that I'll discuss is uniform flow plus doublet. Okay, which you'll see that turns out to be the case of flow past a cylinder. Okay, and in the last superposition, we take the superposition of uniform flow, doublet and also vertex. We will take all the superpositions. In such case, you will get flow past a rotating cylinder. There the stagnation points are much important. Okay, clear? So this is basically the analysis. So if you quickly see what we have done today, we have talked about this nice diagram also which is there. So we have done some revision for some quite time. Then we have seen the case of a doublet. Then we have seen the some mathematical analysis again and the plotting of streamlines in case of a doublet. Okay, normally in potential flow books, I mean in fluid mechanics books, in potential flows, you might have seen this diagram and you might have felt very complicated. How you might have, as soon as you have seen the diagram, you may not understand what is it actually, but now I hope it's very clear to you what is this diagram, what are those circles. Okay, clear? Now similarly, we have seen the case of vertex flows, then we have seen strength of the vertex, some concept of circulation. Okay, so verticity into area of the element we have taken, and basically this stream functions we have generated, I mean it's complex potential function we have done. Then superposition of flows, if you see, we have done uniform flow plus source. Okay, so when you do uniform flow plus source, we have got this particular equation. Then the velocities we have split it using complex numbers analysis and simple equations. Okay, then we have done certain mathematical analysis. Okay, so we have taken one value at ℏ equal to m by 2. So ℏ is equal to m by 2. We have taken this different dimensions. Okay, so we identified what is OA, OB, then DF, all these things. Okay, so half of DE, we have identified all these things, and yeah, these are the things that we have looked upon. So thank you all. Thank you.